there's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of % and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces, or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. There are buildings in the world that are deliberately designed to sway. Why do engineers allow skyscrapers to rock in the wind like living creatures? And what happens if they don't? How do old cars, dismantled bridges, and ocean liners transform into the steel bones of megacities capable of withstanding storms and earthquakes? Behind the scenes of this process are furnaces with temperatures hot as hell, continuous casting machines, and beams as long as a football field. Today, you'll see how metal junk becomes the foundation of skyscrapers. And if you watch till the end, you'll find out why the perfect beam shouldn't be as strong as possible, but properly weak. What's fascinating is that a beam needs to be more than just strong. It needs to be flexible. During high winds, skyscraper tops can sway several feet. The steel frame works like a giant spring. It lets the building breathe and rock without breaking apart. If the beams were totally rigid, the building would just crack during the first storm. The journey of a steel beam for a skyscraper doesn't start in a mine. It starts at massive scrap yards and industrial lots. Modern steelmaking is basically the world's biggest recycling operation. Today's skyscraper steel production often starts not in a blast furnace, but in an electric arc furnace. They load it up with carefully sorted scrap metal and pig iron. Steel scrap is the main ingredient for electric arc furnaces. It's divided into several categories. First, there's home scrap, waste from the steel mill itself, beam cutoffs, foundry leftovers. Second, there's industrial scrap, metal remnants from auto plants or appliance factories. But the most interesting, obsolete scrap. Old bridges, dismantled rails, ocean liners cut into chunks, and millions of scrapped cars. Before entering the furnace, a car goes through a giant shredder that turns the body into fist-sized pieces in seconds. Magnetic separators pull out the steel, separating it from plastic, glass, and non-ferrous metals. While scrap is the foundation, trash alone isn't enough to create the precision steel of skyscrapers. Pig iron must be added to the furnace. It's obtained from iron ore in blast furnaces. Pig iron contains over 2% carbon, which makes it extremely brittle. If you strike a pig iron ingot with a sledgehammer, it can shatter like glass. In the metallurgical process, pig iron plays the role of a clean additive. Scrap can contain unwanted impurities like copper or tin, which degrade the quality of beams. Adding virgin pig iron allows these impurities to be diluted, and the chemical composition of the future steel to be precisely tuned. Metal collection is a full-blown logistics empire. Massive scrap yards are scattered across the country. Magnetic cranes sort metal by grade, because structural beams need steel with low phosphorus and sulfur content. The weight of a single batch loaded into the furnace in a giant steel basket can exceed 100 tons. Picture the thunderous roar as tens of tons of old metal crash into the furnace where a fiery arc is already raging. It's the moment when a city's past, old cars and scrap iron, literally melts down to become its future high-rise skeleton. So they load the furnace with carefully selected scrap metal and pig iron. Massive graphite electrodes descend inside, creating an electric arc with temperatures exceeding 5,400 degrees Fahrenheit. The steel transforms into glowing liquid. At this stage, alloying elements are added to achieve the required strength and flexibility. The process that transforms molten liquid steel into solid billets looks incredibly fascinating and massive. In the past, metal was poured into stationary molds. Workers waited for cooling, extracted the ingots, then reheated them again. It was slow, energy-intensive, and produced lots of defects. Today, the world belongs to continuous casting machines. It's like a giant tower, as tall as a multi-story building. At the very top, they hoist a ladle filled with molten steel at temperatures exceeding 2,800 degrees Fahrenheit. The metal flows downward through a system of intermediate vessels that stabilize the flow and purify it of slag remnants. The heart of the machine is the mold. It's a copper form, constantly cooled by water. When liquid steel enters it, the edges instantly freeze. A solid shell forms, though inside the metal stays liquid, like the filling in a chocolate candy. Next, this endless steel ribbon exits the crystallizer and travels downward through a system of rollers in a curved path. Here, high-pressure water sprays hammer it. This is the secondary cooling zone. The metal solidifies completely, transforming into a solid, glowing hot slab. This process never stops for a second. Fresh steel pours in from the top, while the finished snake crawls out from below. Depending on what we're trying to build, the machine shapes different types of billets. Slabs. These are massive flat plates. If you see a wide steel blanket 12 inches thick and several feet wide, that's a slab. Later, they're rolled out into sheets for ship hulls or car bodies. Blooms. These are thick, square bars, typically 7 by 7 inches. They're the parents of those structural beams used to build skyscraper frames. Their massive size provides enough metal to form powerful I-beams. The most thrilling moment comes at the end of the line, where the endless piece has to be cut into manageable sections. Since the steel is still glowing red hot, that's around 1600 degrees, a regular saw won't touch it. That's where automatic oxygen torches come in. They move in sync with the beam. A stream of pure oxygen under high pressure cuts into the metal, burning through it and creating a perfectly clean cut. At that moment, thousands of sparks fly, and a piece weighing 10 or 15 tons separates from the main flow. Pretty incredible, right? These hunks of metal, still breathing heat, get marked and sent forward to the rolling mills. Thanks to continuous casting, we get metal with a uniform structure, no internal voids. That guarantees the beam on the 40th floor of a skyscraper won't have a single weak spot. First, the bloom passes through rollers that squeeze it, making it longer and thinner. Then, the metal enters universal stands. Here, rollers press the steel simultaneously from above, below, and from the sides. They start squeezing out the middle of the bar, forming a thin wall shaped like the vertical part of the letter I, while leaving massive edges that become the flanges of the beam. Why does a beam look like the letter I? It's a genius way to save metal and weight. The main load in the structure falls on the top and bottom sections. By cutting out metal from the middle, engineers make the beam several times lighter, while keeping 90% of its strength. This allows for lighter and taller buildings. A blank that started out 10 or 15 feet long gets stretched into a massive beam over 150 feet long. It looks like a river of fire. When the rollers press on the steel, they're not just changing its shape, they're healing the metal structure. Under pressure, microscopic pores disappear, and the grains of steel's crystalline lattice stretch in the direction of rolling. This makes the metal way stronger in tension and bending. When the beam already has its perfect I shape, it's still red hot. Now comes the critical moment: controlled cooling. Thousands of nozzles spray a water mist onto the beam. This isn't just a shower. Engineers precisely calculate the cooling rate to get the perfect balance between hardness and toughness. Cool it too fast, the beam can crack under load. Too slow, it'll be too soft. After cooling, the beams pass through a straightening machine, where a series of rollers bend them, eliminating any warping that occurred during cooling. At the end, giant saws, as tall as a person, cut the beam into the required lengths with an incredible screech. These are exactly what we see on construction sites. The steel used to make beams is one of the few materials in the world that can be recycled infinitely without losing quality. Your modern office building could literally be made from melted down cars from the 50s or old ships. It's the circle of metal in a metropolis. Every year, humanity pulls off the same impossible trick. We make ordinary rock flow like water and transform it into the foundation of cities, machines, and entire civilizations. But why does rock, where metal sometimes makes up less than a quarter, hide such colossal power? How does stone travel through hellish temperatures, oxygen explosions, and electric arcs hotter than the surface of the sun to become steel, copper, or aluminum? Behind the scenes of this process, there's a moment almost never talked about. A point of no return where the fate of metal and entire industries is decided. Watch this video to the end, and you'll discover what happens in that split second, and why, without it, the modern world simply wouldn't exist. It all starts with ore, rock that contains the desired metal in the form of chemical compounds with oxygen, sulfur, or other elements. Iron ore, copper ore, aluminum ore. They look like ordinary stones, maybe a bit colorful or heavy, but nothing special at first glance. The problem is that even in rich ore, the useful metal might only be 15 to 30%. The rest is waste rock that has to be separated somehow. Mining ore is already an epic undertaking. Open pit mines reach depths of over 1,500 feet and widths spanning several thousand feet. Massive excavators with buckets the size of a 2-story house tear away rock by the ton in a single scoop. Giant dump trucks with wheels as tall as a 2-story house and payload capacities of 300 to 400 tons haul ore to processing plants day and night. In a year, one large mine extracts tens of millions of tons of rock. The first step in processing is crushing. Massive rocks the size of a car enter crushers that break them down into fist-sized chunks. Then these chunks go into mills, cylindrical drums several yards long, filled with steel balls weighing several pounds each. The mill rotates, the balls drop, and pulverize the ore until it becomes a fine powder. The sound of such a mill, a rumble and clatter you can hear for miles. Now we need to separate the valuable minerals from the waste rock. Different methods are used for this. Flotation is one of the most popular. The crushed ore is mixed with water to form a slurry. Then special chemical reagents are added that make the surface of the metal particles hydrophobic, meaning they repel water. Then air is blown through the slurry, creating bubbles. Metal particles stick to the bubbles and float to the top as foam, while the waste rock settles at the bottom. Magnetic separation works for iron ore. Powerful electromagnets attract the iron mineral particles, and the waste rock just falls away. Gravity separation uses the difference in density. Ore with metal is heavier than waste rock, so on special vibrating tables or in water streams, the heavy particles settle while the lighter ones wash away. After enrichment, you get concentrate, a powder where the useful mineral is now 50 to 70%. But this still isn't pure metal. It's a compound with oxygen or sulfur. You need to remove these impurities and obtain the pure element. Let's take iron as an example, because it's the most common structural metal. Iron ore is mostly iron oxides, iron bonded with oxygen. To get pure iron, you've got to strip that oxygen away. This happens in blast furnaces, massive structures up to 100 feet tall and 50 feet across. A blast furnace runs continuously for years. It's loaded from the top in layers: iron ore, coke, and limestone. Hot air, heated to 2,000 degrees Fahrenheit, gets blasted in from below. The coke burns. The temperature inside the furnace hits 4,000 degrees. At those temperatures, carbon rips the oxygen away from the iron oxide. The iron melts and flows to the bottom of the furnace. The scale of the process is staggering. A single blast furnace consumes 3,000 to 5,000 tons of ore per day, about a ton of coke, and produces 2,000 to 3,000 tons of pig iron. That's iron with high carbon content, around 3 to 4%. The molten pig iron reaches temperatures around 4,000 degrees, a true river of fire flowing from the furnace every few hours. When they open the tap hole, an opening at the bottom of the furnace, the molten metal streams out in a brilliant yellow-white torrent into special ladles or channels. The light is so intense, you have to look through dark goggles. The temperature around it hits several hundred degrees, even from dozens of feet away. The air fills with the smell of hot metal and sulfur. But pig iron isn't steel yet. It has too much carbon in it. It's brittle and won't work for most applications. To make steel, you need to drop the carbon content below 2% and remove impurities like sulfur, phosphorus, and other elements. To do this, they remelt the pig iron in converters or electric arc furnaces. The oxygen converter is a massive pear-shaped vessel, as tall as a 5-story building, that can hold up to 400 tons of molten metal. The converter can be tilted to load pig iron and pour out finished steel. When the vessel is filled with molten metal, a water-cooled lance is lowered into it from above, and pure oxygen is injected under pressure. Oxygen is blown through the molten metal at a rate of hundreds of cubic meters per minute. Carbon burns off, creating an enormous amount of gases and sparks that shoot out of the converter's mouth like a volcanic eruption. The temperature of the molten metal rises from the energy released by burning impurities. The entire process takes about 20 minutes, during which 300 tons of pig iron are transformed into steel. Electric arc furnaces are used to melt down scrap metal. Massive graphite electrodes, up to 2 feet in diameter and several yards long, are lowered into the loaded scrap. An electric arc ignites between the electrodes and the metal, reaching temperatures up to 11,000 degrees Fahrenheit, hotter than the surface of the sun. Power consumption hits megawatts. A single furnace can burn through as much electricity as a small town. The metal melts, boils, violently reacts with added flux agents. Slag, a molten mix of oxides and silicates, floats to the surface of the metal and captures impurities. It's regularly tapped off separately. When the metal composition hits the target specs, the melt is poured into a ladle holding dozens to hundreds of tons. This process runs simultaneously at dozens of plants around the world, non-stop, 24 hours a day, 365 days a year. Every year, humanity produces around 2 billion tons of steel. That's roughly 550 pounds for every single person on the planet, including infants. 2,000 million tons. Try to wrap your head around that number. Non-ferrous metals are extracted similarly, but with nuances. Copper often occurs as sulfides, compounds with sulfur. First, the ore concentrate is roasted in furnaces at temperatures around 2,700 degrees Fahrenheit to oxidize the sulfur. Then it's melted at nearly 5,400 degrees, producing matte, an alloy of copper and iron sulfides. The matte is blown with oxygen in a converter, removing iron and residual sulfur, yielding blister copper at about 98% purity. But electronics and wiring need copper at 99.99% purity or higher. This is achieved through electrolytic refining. Blister copper plates get dunked into baths of copper sulfate solution, and an electric current runs through them. Copper dissolves from the anode and settles on the cathode as absolutely pure metal. Impurities either sink to the bottom of the bath or stay in the solution. The process is slow, but it produces the purest copper. Aluminum, that's a whole different story. It's the most abundant metal in Earth's crust, around 8%. But it's so tightly bound to oxygen that extracting it chemically is nearly impossible. Aluminum comes from bauxite, an ore containing aluminum hydroxide. First, bauxite gets treated with alkali under high temperature and pressure to produce pure aluminum oxide, alumina. Then this alumina gets melted through electrolysis in baths of molten cryolite at temperatures around 4,000 degrees Fahrenheit. A massive electric current, tens to hundreds of thousands of amps, runs through the molten mixture. Oxygen gets released at the anode and burns off, while pure aluminum settles at the bottom of the bath. Producing 1 ton of aluminum consumes roughly 15,000 kilowatt-hours of electricity. That's about what an average apartment uses in a year. Aluminum plants get built near massive hydroelectric dams because you need cheap electricity in enormous quantities. One modern plant produces 1 million tons of aluminum per year and consumes as much electricity as a city of 1 million people. This is an industry that literally converts electricity into metal. Titanium extraction is even more complex. Titanium ore, titanium dioxide, first has to be converted into titanium chloride, then reduced with magnesium or sodium in sealed reactors at temperatures around 2,000 degrees. What you get is titanium sponge, a porous material that then gets remelted in vacuum arc furnaces multiple times to remove impurities. That's why titanium costs tens of times more than steel. Every year, steel giants weighing hundreds of tons are born across the world, chunks of metal heavier than 40 elephants combined. But here's the question. How do you transform a 400,000-pound red-hot block into a perfectly precise component for a nuclear reactor or aircraft turbine, where even a millimeter of error means catastrophe? Only a handful of facilities and machines on Earth can pull this off. Presses generating tens of thousands of tons of force, buried stories underground. Why a seamless steel shell matters more than any armor, how nations compete for control over these technologies, and what critical weakness of modern civilization heavy forging conceals. You'll discover by the end of this video. If you watch till the end, one fact will change how you think about the strength of metal forever. A chunk of steel weighing over 200 tons. That's like 40 elephants stacked together. Now imagine you need to transform this giant metal block into a high-precision component for a nuclear reactor or aircraft turbine. Sounds impossible? This is exactly what happens every day at the world's largest forging plants, where force, engineering, and precision create genuine metalworking miracles. Among the industry's most remarkable facilities, Japan Steelworks in the city of Muroran on Hokkaido Island holds a special place. Founded in 1907 with participation from British companies Vickers and Armstrong Whitworth, this plant today controls around 80% of the global market for large forged components for nuclear power plants. Here are hydraulic forging presses ranging from 3,000 to 14,000 tons of force, with the largest capable of working steel ingots weighing up to 600 tons. What makes this plant unique? First and foremost, the ability to manufacture nuclear reactor vessels as single, seamless structures. This is critical for safety. Welded joints are weak points where radiation can leak. JSW remains one of the few manufacturers in the world capable of creating such components without any welding. Modern giant presses are engineering masterpieces in their own right. Take, for example, the Schultz steel press in California, which delivers 40,000 tons of force. This machine weighs over 2,650 tons, stands 60 feet tall, and is sunk 8 stories into the ground. To support it, you need a concrete foundation almost 2 inches thick, reinforced with rebar up to 4 inches in diameter. The press is controlled by 12 electric motors, each pumping out 1,200 horsepower, and 24 main hydraulic pumps. When those pumps kick in, the machine can stop 1,700 tons of moving parts to within 1/10 of an inch, all without hydraulic shock that could damage the structure or the workpiece. The precision of this giant is staggering. It can control position to within limits and pressure to within 300 tons of the target value. It's like trying to stop a train 1 centimeter from the mark, over and over, with absolute reliability. The process of creating a massive forged component starts long before the metal ever sees a press. First, a huge steel ingot gets cast. Modern third-generation nuclear reactors need ingots weighing 500 to 600 tons. That's a colossal engineering challenge, making, heating, and moving this little grain of steel that has to stay hot during transport from the steel mill to the forging shop. The steel for these gigantic components has to be flawless. Japan Steelworks uses cutting-edge purification technology, argon blowing to remove impurities, and precise additions of manganese, chromium, and nickel to hit the exact hardness and strength targets. Every single step of the process gets monitored with maximum attention to detail. Once the heated ingot hits the press, the most spectacular part of the process begins. Giant hydraulic pistons, each the size of a small room, slowly descend with incredible force. The metal, glowing red hot, starts to deform plastically, taking on the desired shape. This isn't a quick strike, like old-fashioned hammers. It's controlled, massive pressure that lasts seconds or even minutes. During the forging of a 200-ton workpiece, it needs to be rotated periodically to ensure even processing from all sides. Special manipulators handle this, enormous mechanical arms that can carefully rotate the white-hot metal giant. These manipulators themselves weigh dozens of tons and are controlled by advanced coordinate systems, ensuring millimeter precision even when working with such colossal masses. Between passes under the press, the workpiece can be returned to the furnace to maintain the required temperature. Forging a large part can take hours or even days, depending on the complexity and size of the final product. The result of this titanic effort? Components our lives literally depend on. Nuclear power plant reactor vessels weighing over 500 tons, capable of safely containing nuclear reactions for decades. Steam turbine rotors weighing over 200 tons, spinning at tremendous speeds, generating electricity for millions of homes. Components for aircraft engines that withstand extreme temperatures and stresses. For the maritime industry, they manufacture crankshafts for ship engines and steering system components weighing up to 300 tons. These parts are used on the world's largest container ships and tankers, ensuring reliability during years of voyages at sea. You'd think forging is just applying force to metal, but it's actually a much more complex science. When metal deforms under immense pressure, its crystalline structure changes. The steel grains align along the load lines, creating a fibrous structure similar to wood. This directionality makes forged metal far stronger in the direction of the fibers than cast steel. Temperature plays a critical role too. Steel that's too hot can become too soft and lose strength. Too cold, it cracks under the press. Engineers must know exactly what temperature to work with each alloy to achieve optimal properties. After forging, parts go through heat treatment, controlled heating and cooling to hit the right hardness and flexibility. Then comes rigorous inspection, ultrasonic scanning to catch internal defects, X-rays, mechanical testing. Not a single hairline crack or void can slip through unnoticed. While Japan's Japan Steelworks dominated this field for years, competition's ramped up lately. China poured massive investment into heavy forging capacity. The biggest Chinese presses hit 80,000 tons of force. These are the most powerful machines on Earth, letting the country be self-sufficient in manufacturing components for nuclear power and aerospace. France's Framatome and 2 more Chinese companies round out the short list of manufacturers capable of creating the largest single-piece components for nuclear reactors. This is a global game where heavy machinery capabilities directly impact a nation's energy and defense independence. The history of heavy forging goes back to World War II, when Japan Steelworks manufactured the barrels for the largest guns on the battleship Yamato. Tragically, during an Allied air raid in July 1945, 200 workers at the main plant in Muroran were killed. But the company was reborn and transformed into a peaceful metalworking giant. Today, these technologies continue to evolve. Back in the 1950s, some experts predicted that aircraft manufacturing might need presses capable of 200,000 and 250,000 tons. Such machines still haven't been built. Even the Chinese giants are half that size. But progress doesn't stand still. Tesla has proven that manufacturing massive one-piece components can revolutionize production. The next generation of presses might actually reach that kind of incredible power. Sadly, not every country held on to its heavy forging capacity. The United States, once home to the world's most powerful presses, lost the ability to make the largest ingots. America's biggest steelmakers, like Bethlehem Steel, could only produce ingots up to 380 tons. Not enough for modern needs. That means the US depends on imports for critical components in nuclear power plants and heavy industry. Britain ran into problems too. Sheffield Forgemasters, the company that made components for the Royal Navy's submarines, planned to install a new 15,000-ton press back in 2010. The government initially allocated £80 million, but later cancelled the funding. This limited the country's ability to manufacture the largest nuclear power components on its own. Behind all this colossal machinery are people, engineers, metallurgists, press operators. Their experience and skill are invaluable. A forging master at these giant plants makes adjustments based on decades of experience. He knows how each alloy behaves, how long to keep it under the press, when to rotate the workpiece. Every year, the world mines millions of ounces of a metal most people never even think about. But without it, modern civilization would literally grind to a halt. What if I told you there's a metal hiding in every car that can absorb hydrogen hundreds of times its own volume, operate at temperatures over 5,000 degrees Fahrenheit, and cost more than gold? Palladium seems invisible, but it's what cleans the exhaust from millions of vehicles, drives key chemical reactions, and determines the price of entire industries. Where does it come from? Why is there so little of it? And what hidden detail at the end of this video will change how you think about this metal forever? Stick around to find out. Palladium is a chemical element from the platinum metals group that combines rarity, high chemical stability, and exceptional physical properties. In the periodic table, it has atomic number 46 and a silvery white color that persists even after prolonged exposure to air. At a density of around 7 pounds per cubic inch, It's lighter than platinum, yet strong enough to withstand significant mechanical stress. Palladium's melting point sits at approximately 2,830 degrees Fahrenheit, and it boils at temperatures exceeding 5,400 degrees Fahrenheit, making it suitable for high thermal load applications. One of palladium's most fascinating features is its ability to absorb hydrogen in amounts hundreds of times greater than its own volume. At room temperature, the metal literally pulls hydrogen atoms into its crystal lattice, forming solid solutions. This property is actively used in hydrogen purification technologies, membrane systems, and alternative energy research. Palladium maintains its stability and doesn't crumble, which sets it apart from many other metals. The industrial importance of palladium is enormous. The bulk of global consumption goes into catalytic converters for automotive exhaust systems. In these devices, palladium accelerates the oxidation of carbon monoxide and unburned hydrocarbons, converting them into less harmful compounds. A single passenger car might use only a few hundredths of an ounce of the metal, but with millions of vehicles in play, total demand hits tens of thousands of pounds per year. It's this industry that makes the palladium market incredibly sensitive to shifts in global auto production and environmental regulations. Beyond the automotive world, palladium is everywhere in electronics. It shows up in multi-layer ceramic capacitors, contact assemblies, connectors, and microchips. Thin palladium coatings shield components from corrosion and wear, maintaining stable conductivity even after thousands of power cycles. In electronic components, the metal's mass is usually measured in fractions of an ounce, or even grains, but collectively these amounts carry serious economic weight. Jewelry wouldn't be the same without palladium. It's added to gold alloys to create white gold without using nickel, crucial for people with sensitive skin. Pure palladium is used to make rings, earrings, and watches because it's lighter than platinum and more comfortable to wear. Palladium pieces hold their shape, don't tarnish, and rarely need polishing. Geologically speaking, palladium is pretty rare. Its average concentration in Earth's crust is just a few millionths of a percent. Major deposits are tied to magmatic complexes and sulfide ores, where palladium occurs alongside platinum group metals, nickel and copper. Mining often takes place at great depths, sometimes several thousand feet below the surface, which makes the process significantly more complex and expensive. Because of this, the price of palladium can fluctuate sharply depending on the political stability of mining regions and the state of the global economy. The chemical behavior of palladium makes it valuable in laboratory practice. It's one of the key catalysts in organic synthesis reactions, particularly in carbon-carbon bond formation processes. Thanks to this, palladium plays an important role in the production of pharmaceuticals, agrochemicals, and specialty polymers. Even microscopic amounts of the metal, measured in milligrams or grains, can substantially impact the speed and selectivity of reactions. Palladium's physical properties are equally noteworthy. It responds well to cold working, rolls easily into thin sheets, and draws into wire. From a single ounce ingot, you can produce a sheet covering several square feet. At the same time, the metal maintains high electrical and thermal conductivity, making it useful in specialized technical applications. Palladium is almost never mined by itself. It's a byproduct of nickel, copper, and platinum metal extraction. Everything starts in underground or open pit mines, where sulfide ore is pulled from depths of hundreds or thousands of feet. The ore is crushed and ground into a fine powder, then mixed with water and reagents and subjected to flotation. The result is a concentrate enriched with copper and nickel sulfides and traces of palladium. Next, the concentrate gets roasted in furnaces at temperatures exceeding 1600 degrees Fahrenheit, stripping away sulfur and organic residues. The resulting material is melted, separating into a metallic phase and slag. At this stage, palladium is still mixed with other platinum group metals. Separation begins at refineries, where alloys are dissolved in acids and subjected to multi-stage chemical purification. Platinum, rhodium, and iridium are precipitated sequentially, while palladium is isolated as salts, which are then reduced to metal. The final stage of palladium extraction begins when, after a long chain of chemical purification, the metal has been separated from other platinum elements and exists as salts or spongy precipitate. This material is thoroughly rinsed with distilled water to remove traces of acids and impurities, then dried in furnaces at temperatures of several hundred degrees Fahrenheit. It looks like a gray-black powder with very low bulk density, which doesn't yet have the properties of compact metal. Next, the powder or palladium sponge is fed into melting facilities. Most commonly, induction or electric arc furnaces are used, where the metal is heated in crucibles made from inert materials. The atmosphere inside the furnace is monitored especially carefully. Argon is introduced, or the space is evacuated to prevent oxidation and losses. The temperature is gradually raised above 2,800 degrees Fahrenheit until the palladium particles fuse into a uniform molten mass with a mirror-like surface. When the metal is fully molten, it's held in the furnace for a set period to even out the composition. Even traces of other metals are measured here in fractions of an ounce per ton, so samples can be pulled directly from the melt for lab analysis. If purity doesn't hit the target level, the melt goes back for additional refining. Only after confirming readings above 99.9% is the palladium cleared for forming. To produce ingots, the liquid metal is carefully poured into preheated graphite or steel molds. The weight of these ingots can range from a few ounces to tens of pounds, depending on customer needs. Cooling happens under controlled conditions to avoid internal stress and cracks. After solidification, the ingots are removed, weighed, marked, and the chemical composition is checked one more time. If palladium is destined for catalysts or the chemical industry, it might skip the ingot stage entirely and be turned straight into powder. To do this, the metal is dissolved again, then reduced under controlled conditions to produce particles of a specific size. This powder gets packed into airtight containers, where every single gram carries serious value. Global palladium production is typically measured in the hundreds of thousands of troy ounces per year. On average, worldwide output hovers around 6 to 7 million ounces annually, with more than 2/3 of that volume coming from just 2 countries. Another key figure, secondary recycling, mostly from used automotive catalytic converters, accounts for 25 to 30% of global supply. By comparison, for many other precious metals, the recycling share is significantly lower. In your average ore, the palladium content is incredibly tiny. We're talking a few hundredths of an ounce per short ton of rock, sometimes even less. That means to get just 1 pound of pure metal, you need to process thousands of tons of ore. That's exactly why production costs are so sensitive to energy expenses and logistics. Picture an industrial world where you need to shape and size the toughest materials. Think hardened steel or high-strength alloys. To drill, mill, or cut one metal, the cutting tool itself must be made from a material with extreme hardness, far exceeding the part being worked. In this battle for dominance over material strength, the invisible but indispensable hero is tungsten carbide tooling. Without these materials, the modern precision, speed, and efficiency of the machine-building industry would be impossible, from manufacturing aircraft engines to producing the tiniest electronic components. If you're searching for the foundation to build a tool capable of outperforming any other, you need to start with this element. Tungsten occupies a unique position where its physical properties simply have no equal. Meet the main superpower: heat resistance. Tungsten is the absolute, unshakable champion among all known metals for melting point. Picture this: its melting point reaches a phenomenal 6,192 degrees Fahrenheit. To put that scale in perspective, iron, considered strong and refractory, already melts at a temperature barely exceeding 2,700 degrees. This extreme temperature resistance is direct proof of the extraordinary strength of its internal atomic bonds. Tungsten simply refuses to surrender to heat, making it irreplaceable for tools operating under extremely high thermal stress. But its advantages go way beyond just temperature. Tungsten is the perfect material for tooling work, thanks to two other key characteristics. First, incredible density. It's extraordinarily heavy, almost 1.7 times denser than lead. This mass, built into a cutting tool, provides the necessary inertia and stability, even at dizzying cutting speeds. A tool made from it doesn't vibrate or deflect, guaranteeing surgical precision. Second, geometric reliability. Tungsten has a minimal coefficient of thermal expansion. This means that when a cutter or drill heats up to hundreds of degrees during metal machining, it maintains its geometric form with micron-level accuracy. Zero creep or deformation. This stability is a critical condition for precision engineering. But there's one catch. Pure tungsten on its own, while refractory and dense, just isn't hard enough. And worse, it's prone to brittleness for direct use as a cutting tool. Its potential only fully unleashes when it transforms into its superhero form. Its true, unmatched power is released when it enters a powerful chemical reaction with carbon, forming the legendary tungsten carbide. This is a ceramic material produced by heating a mixture of tungsten and carbon powders to high temperatures. Tungsten carbide structure is characterized by covalent bonds, which are far stronger than typical metallic ones. These tungsten carbide crystals are among the hardest known materials on the planet. Their hardness on the Vickers scale exceeds 2500 HV, falling just slightly short of diamond, which clocks in at 10,000 HV, and cubic boron nitride. Compared to the hardest hardened steel, tungsten carbide is roughly twice as hard. Although tungsten carbide is incredibly hard, it's also very brittle, similar to ceramic. If you used pure tungsten carbide for a cutting tool, it would simply crack during the first impact load or vibration. To eliminate this brittleness and give the material the necessary toughness, meaning the ability to absorb impact energy without failing, a metallic binder phase is used, most commonly cobalt. How do you create a material that only melts at 6,000 degrees Fahrenheit into the form of a perfectly precise tool? The answer is simple. Conventional casting doesn't stand a chance. Tungsten carbide is too stubborn and won't yield to standard industrial furnaces. So to create these cutting titans, inserts, end mills, drill bits, you need high-tech engineering wizardry, powder metallurgy. First, we take two key ingredients: ultra-fine tungsten carbide powder, which is our super hard foundation, and cobalt powder, our future cement and shock absorber. They're carefully mixed in a precise proportion. Balance is critical here. Less cobalt gives maximum hardness, but brittleness. More cobalt makes the tool tougher and more impact resistant, though slightly less hard. After mixing, the blend is pressed under colossal pressure, forming perfectly precise blanks for inserts or drill bits. It's like creating a raw, not yet fired, but already shaped product. But the real transformation happens in special vacuum or hydrogen furnaces during a process called sintering. The temperature slowly but steadily climbs until it exceeds a critical point. At that moment, cobalt, being the more accommodating metal, melts. Meanwhile, the super-hard tungsten carbide crystals remain completely unmelted. This is liquid phase sintering. Molten cobalt, like a river, floods every gap between tungsten grains. It acts as a binding agent, tightly enveloping each super-hard grain. The structure takes on the appearance of a perfect brick wall, where tungsten grains are the bricks and cobalt is the mortar. After cooling, we get a cemented carbide that demonstrates phenomenal synergy. It has hardness comparable to diamond, but thanks to the cobalt matrix, it has enough strength and toughness to withstand the impacts and vibrations that are inevitable during cutting. It's this perfect combination that allows these unassuming tools to cut even the toughest hardened steel and exotic alloys without any noticeable wear. Tungsten carbide tooling is so critical that roughly 50% of all tungsten mined in the world goes into making it. This underscores its strategic importance to the global economy and industry. The applications of these unsung heroes span virtually every industry that requires metalworking. Milling cutters, lathe tools, drill bits, and reamers with carbide inserts form the backbone for manufacturing engine blocks, transmissions, turbines, and other high-precision components. They allow cutting at high speeds, dramatically boosting productivity. Mining and extraction. Drill bits and inserts for mining equipment, built on tungsten carbide, are essential for penetrating the hardest rock formations and granite. No modern mining or oil and gas drilling operation is possible without this technology. Machining titanium and heat-resistant nickel alloys, used in turbine blades, demands tools that can withstand extreme temperatures and chemical interaction. Carbide tools, often with additional coatings like titanium nitride, are the only practical solution. Tungsten carbides are used to create dies for stamping, wire drawing dies for wire production, and wear-resistant components in pumps and valves, where abrasion resistance is essential. The total value of the global market for tungsten carbide-based hard alloys and tools made from them is estimated at tens of billions of dollars annually. This is a high-margin industry, critically important for manufacturing, because quality tooling, while expensive, pays for itself many times over through increased machining speed and precision. The service life of a cutting carbide insert can be extraordinarily long. In some cases, an insert can machine several tons of material before it needs replacement or resharpening. This far exceeds high-speed steel, which requires frequent replacement. Tungsten is a strategic and relatively rare metal, making its recycling vitally important. According to estimates, a significant percentage, sometimes as much as 30%, of the tungsten used in manufacturing new hard alloys comes from recycled worn-out tools. This saves energy and reduces dependence on primary ore extraction. What if I told you that inside the most dangerous machines on the planet hides a steel secret that can only be created once, and a mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would shatter mountains? This giant is born in fire, exceeding 5,000 degrees Fahrenheit, endures months of forging, blows of tens of thousands of tons, and thermal shocks that would explode ordinary metal into fragments. Stick around till the end. You'll discover what these monoliths are actually built for, and why, without them, the modern world would simply grind to a halt. It all starts in the foundry. To create a monolithic ingot, you need liquid steel of impeccable quality, poured into a mold in one continuous stream. This is a stage that demands maximum coordination, because we're talking about thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was a record-breaking pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully handled the pouring of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level that meets the strictest customer requirements, for example, for reactor components. This means minimizing impurities, gases, and slag. A continuous pour ensures that there won't be any layered defects or boundaries in the ingot structure that would reduce its mechanical strength. During casting, the steel must be fully degassed. Oxygen and nitrogen levels are controlled at levels often not exceeding 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Immediately after pouring the molten metal, which can exceed 2,700 degrees Fahrenheit, time becomes the most critical factor in this process. Unlike small ingots that can cool quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it leads to massive internal stresses, cracks, and structural defects, because the outer layer solidifies while the steel inside is still liquid. To ensure uniformity of the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, incredibly slow process, during which the steel gradually solidifies, dropping to a temperature of around 2,000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees a high-quality macrostructure, which is the key to the strength of the future component. Only after this lengthy solidification period is complete, the steel monolith, which after shrinkage and removal of the defective top portion weighs approximately 320 tons, is carefully extracted from the ground. The extracted ingot, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is required. Forging 500-ton ingots demands hydraulic presses with working forces ranging from 10,000 to 20,000 tons. For example, forging the largest reactor components requires presses with a capacity of 40,000 tons. Before forging, the ingot is again carefully heated in specialized furnaces. This process can take weeks to guarantee uniform heating throughout the entire volume of metal. The forging itself is done on giant hydraulic presses capable of creating pressure in the tens of thousands of tons. The press breaks down large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal gains a directional fibrous structure, which significantly increases its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Each press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the furnace for heat treating ingots during a 2-week cycle can exceed 100,000 kilowatt-hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature deviation in the furnace throughout the entire volume can be only 40 degrees, which requires the use of high-precision multi-zone control systems. After shaping the ingot, we move to heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. A multi-ton steel monolith that's just survived months of casting and forging is like a clumsy giant whose final character hasn't formed yet. It's strong, but its internal structure is still chaotic, riddled with invisible internal stresses. The first step is normalization, or, as we call it, homogenization. The idea is simple. We basically stir the metal structure so it becomes absolutely uniform throughout the entire volume. This ensures that at every point in the workpiece, both on the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so your cake bakes perfectly. Then comes the most dramatic moment, quenching. The workpiece is heated to a very high temperature, bringing it to peak plasticity. And then, rapidly, but under strict control, it's cooled. This could be a water or oil bath. This shock to nature transforms the soft steel structure into something maximally hard and strong. This gives the part its core fighting strength, but there's one side effect. The metal becomes brittle as glass, and massive internal stresses appear. If you leave it in this state, it can crack from the slightest impact. That's why the final, and most humane stage is tempering. The piece is carefully reheated, but this time to a much lower temperature. The goal isn't to change the strength, but to release the internal stresses that formed during rapid quenching. This process is like taking a deep breath after stress. It increases the steel's toughness, making it resistant to impacts and loads, eliminating brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants for, into which so much time and resources have been invested? They become critically important components in industries where the price of failure is unacceptably high. For example, in nuclear power, these ingots are transformed into key components of high-pressure reactors. Picture this: pressure, temperature, and radiation demand absolute reliability. And there can't be any seams or welds that might give way. You need just one thing: a solid, continuous monolith capable of withstanding extreme loads for decades. In heavy machinery, these giants become frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A frame that won't deform under thousands of tons of load has to be cast in one piece. And of course, there's power generation, rotors for the largest steam turbines, or crankshafts for massive marine engines that drive supertankers and container ships. In these components, you need guaranteed strength against bending and secondary loads, and only steel produced through this incredibly complex process can deliver that.